Hi, I am Anirudh, and in this video I shall briefly explain how transition metal dichalcogenides or TMDs came into existence in the era of CMOS scaling. The title of this talk is CMOS scaling, the era of transition metal dichalcogenides. The outline of this talk is as follows. The talk is divided into three sections. Primarily, in the first section, I shall introduce the idea of transition metal dichalcogenide and challenges. And in the latter two sections, I would cover two recent innovations in the area of transition metal dichalcogenides. The first one being scaling up this transition metal dichalcogenide wafers to 300 millimeter. That is the typical wafer size, and the performance of NMOS and PMOS and its reliability on a wafer scale level. And in the second uh, part of the latter section, I will discuss a method to develop a 1 nanometer effective oxide thickness using two methods, first being silicon seed and the second being the ALD of ALOX. And In the last section, I shall present a conclusion of the papers. So moving forward, in the first section, introduction, the idea of developing thinner and thinner channels eventually led scientists to look at graphene as a channel material for transistors. This is because graphene offered significantly higher mobility. However, graphene as a channel material posed several challenges. The first point is that graphene is a zero band gap material. That is, switching off was an issue in graphene, which resulted in a significant ion to eye off and a very high standby power. So, graphene could not be used there. And the second challenge in graphene was the idea of band gap engineering. The idea of band gap engineering in graphene led to significant reduction in channel mobility, which was undesired. So the idea of graphene as a channel material did not survive for a long time. We then moved forward to this idea of transition metal dichalcogenides, TMDs. These are typically compounds with formula MX2, where M is a transition metal from the group 4, 5, and 6 of the modern periodic table, and X is a chalcogenide, which is an element of group 16, which is typically either sulfur, selenium, or tellurium. And this is the structure of a MOS2 crystal. So it has a planar lattice and it has a good mobility, as we shall see later. So the properties of TMDs that were favorable for CMOS are as follows. So as we started thinning down silicon wafers, silicon started showing degradation in channel mobility. That is, its mobility came to the order of 150 centimeter square per volt second. And since we were requiring monolayer thicknesses of sub 1 nanometer for high electrostatic control, silicon could not be used due to its degraded mobility, and we were looking for alternatives. And the biggest advantage of transition metal dichalcogenides is its band gap. It's similar to silicon. And the most advantageous property of TMD is that its surface is free of dangling bonds. That is, it's fully passivated, which provides a cleaner interface. And this is a diagram that demonstrates the idea of CMOS scaling, the major innovations that have taken place, apart from just mere dimension reduction to engineering, say in effective oxide thickness by introducing high K dielectrics and metal gate, and alteration to device topology, SOI, FinFET, nanowires, nanosheets, and the idea of 2D materials also being here. And the fabrication of TMDs is relatively interesting. I shall just briefly touch upon two methods. So the first method was proposed by Intel in a single layer planar device fashion, and this was basically done using MOCVD, that is metallo-organic chemical vapor deposition. So we shall look at this later. So I'll skip this part now. And the second one was in a nanosheet fashion proposed by TSMC at the 2023 IEDM. The 2D channel material was deposited using CVD or film transfer. So as you can see in this, MOS2 layers were chemically vapor deposited on this sacrificial layer, which was then etched out and the dielectric was filled, similar to the way a nanosheet is formed. This was proposed by TSMC. And the common techniques of fabrication of TMDs are as follows. The first is molecular beam epitaxy process. So this is a relatively slow process. The second one is a physical vapor deposition, which is used for multi-layer films. And the third one is a chemical vapor deposition, which results in best outcomes. The challenges for CMOS compatible processes, particularly with respect to TMDs, is that there is a requirement of high quality epitaxial growth of TMD at sub 450 degrees centigrade for front end of the line processing, and there is a requirement of low temperature interfacial layer deposition. And we need to come up with better choices for sacrificial or supporting layer without impacting the TMD during layer edge. And moving forward, the challenges of TMD is that the typical mobility of CVD grown MOS2 is of the order of 40 centimeters square per volt second, whereas that of a 2.5 nanometer thick silicon is of the order of 150 centimeters square per volt second. And this is a plot showing mobility as a function of channel length for TMDs as a function of various literature that has been reported. And similarly, the contact resistance of TMDs is an issue since the metal to TMD interface is having a slightly higher Schottky barrier than a metal to silicon contact. The contact resistance is slightly higher, and the contact resistance of TMDs is a strong function of gate bias. And this is a plot showing contact resistance as a function of channel length. Both of these plots are taken from this 2d.stanford.com. It gives an extensive plot of TMD properties. And another challenge is with respect to the gate dielectric. So the gate dielectric of TMDs came with various issues such as insulator defects, channel defects, and the subthreshold slope of most general TMDs is typically high, and often TMDs channel have a hysteresis loop, and we shall see later how using interesting seed crystal technique and ALOX atomic layer deposition, we are able to achieve a good subthreshold slope and lower hysteresis later in the second paper. So now we shall move on to the second part, that is the discussion on exploring manufacturability of novel 2D channel materials for 300 millimeter wafer scale 2D NMOS and PMOS using MOS2, WS2, and WSC2, presented by Intel and IMEC at IEDM 23. So the proposed structure of the transistor is as follows. The proposed structure by Intel is that of a 2D stacked nanosheet complementary field effect transistors. This was the first work on scaling 2D materials to 300 millimeter. The advantage of this scaling is that it enables highly scaled gate lengths and it allows more channels per stack, thus giving a higher current for a given overdrive. And this is the proposed structure. Moving forward, the fabrication has been done on a planar process for the evaluation of transistor performance. And the transistors were evaluated on two types of device. The first one being a global bottom gate device with an effective back gate oxide thickness of 50 to 62 nanometer. That is this structure. And the second one is a double gate which has a effective oxide thickness combined of top and bottom gate of 2.2 nanometer. The process flow is as follows. We start off with a silicon wafer. We do a blanket well implantation. And typically, if you want a double gate device, you form the local bottom gate formation and do a bottom gate degeneration doping. And the bottom gate dielectric is deposited, followed by 2D channel deposition. This is done using MOSFET, as we shall see later. And the top gate dielectric is deposited and patterning of the active region is done. Then the trench to edge contact formation is done. Then trench top gate formation is done. Then via back gate formation is done. And then via and pad formation is done. So the TMDs are deposited using the process of metallo-organic CVD. This is the typical structure of a MOCVD chamber. The advantages of a MOCVD over atomic layer deposition is that ALD is incompatible for direct growth of TMDs on amorphous substrate, and it is difficult to scale to 300 millimeter. So MOCVD offers a significant advantage. And in the paper, there are two types of grains that have been analyzed. That is the size of the crystal. The first one is a small grain size, that is of the order of 100 nanometer, and the second one is a large grain size, which has grain sizes of the order of 1 micrometer, and each of these has its own advantages. We shall see. The first one we shall see now is an NMOS. The candidates that were used for making NMOS transistors were MOS2 and WS2. The contacts for this NMOS device were made using titanium, which were deposited using physical vapor deposition. And it was observed that small grain MOS2 has lower mobility and higher subthreshold slope compared to small grain WS2. This is because of the higher defectivity due to the smaller grain size of MOS2. Larger grain MOS2 has better performance. And it was observed that as a function of channel length, MOS2 showed higher current due to lesser contact resistance. As evident from this graph, the contact resistance of MOS2 is much lower than that of WS2, and due to this, the current drive of MOS2 was higher than WS2, as seen from this. And it was observed that increasing grain size improved NMOS performance. This is because the lower defectivity was observed due to better crystallinity of large grain films, and it was also empirically computed that the mobility of large grain was about 4 times that of small grain, and the current drive of large grain MOS2 under large gate bias was observed to be of the order of 10 microampere per micrometer, whereas that of small grain was much lower. And it was observed that large grain MOS2 offered a reduction of about 40% in subthreshold slope compared to small grain MOS2, and WS2 already had a much lower subthreshold slope. And Imax, the maximum current that was reported, was also 10 times larger for large grain compared to small grain, and the maximum current that was reported was about 100 microampere per micrometer for large grain MOS2. And these are the results for the NMOS characterization. Moving forward to the PMOS, the most common used TMD for PMOS is WSE2, and the contacts are also typically the same, made of ruthenium. And as we saw earlier, the large grain current is about 5 times that of the small grain current. This is due to the better crystallinity of the large grain crystals, and this is analogous to the NMOS case. And the mobility also is much higher here. The mobility is 30 centimeters square per volt second. Just to add here, the mobility of the large grain crystal was observed to be about 7 centimeters square per volt second. The mobility in the PMOS case was higher, of the order of 30 centimeters square per volt second. And as we saw earlier, as in the case of NMOS, increasing grain size improves PMOS performance, and the maximum current drive here, as we see, is of the order of 100 microampere per micrometer for a channel length of 135 nanometer. And the PMOS was studied for a various set of configurations. They experimented with thick channel, thin channel, and asymmetric thickness. It was observed that thick channel resulted in a high off current, and a thin channel offered a very low off current and a very low dibble. However, an asymmetric thickness channel offered a low ion, and it was quoted that the thinner channels show an IOF of sub 20 picoampere per micrometer and lower dibble. So this was the advantage of a thin channel. And it was also observed that the PMOS device showed 2 types of behavior. That is, on switching the source and drain. The first type was tested on a symmetric device, that is a fully continuous uniform 2D film between the source and the drain, and the source and drain were switched, and it was observed that the performance was almost the same upon switching. And in another case, when there was asymmetric channel, asymmetric channel is characterized by a difference in 2D layer width, or the deposition thickness difference at the source and the drain of the TMD, and it was observed that the asymmetric deposition resulted in a very clear difference and a hysteresis in the case of MOS2 asymmetric crystals. And moving forward, they also experimented using small grain WS2 to check for PMOS kind of performance. It was observed that WS2 showed ambipolar behavior as is seen here with very low on currents, that is of sub 100 nanoampere per micrometer. So it was quoted that WSE2 performs best as a PMOS candidate. Both the contacts were made of ruthenium only. And continuing the case as in case of an NMOS, the higher Imax is reported for large grain compared to small grain. This is because of higher crystallinity. And the transistors were also tested for reliability. It was observed that MOS2 showed large degradation, shown by the yellow curve here, and the WS2 showed worst behavior, whereas WSE2 showed lower NBTA, which is a good performance metric for PMOS. And it has been stated that the difference in BTA for these three TMDs are a consequence of different band offsets and a consequence of different interactions with the top aluminum dioxide dielectric, and thus can be explained. And in conclusion, this paper successfully shows a first look at 300 millimeter wafer scale TMD candidates. The key highlight here is the growth process of TMDs is using a simplified direct deposition technique. Going forward, we need to look at a way to develop a uniform crystal growth of TMDs and come up with specialized processes to enhance gate oxide nucleation on these passivated TMDs, and also possibly look at atomic etching to integrate thin layers. And this gives the overall highlight of the paper. The best performing PMOS candidate WS2 as a function of gate bias IDVG curve, and the best performing NMOS MOS2 characterization IDVG curve. And this is a plot of on current versus subthreshold swing. This work is somewhere here. High subthreshold swing and uh, lower ion compared to a lab which has higher on current for the similar subthreshold swing. Whereas the target we want is a very high on current and a very low subthreshold swing. There needs to be a lot of work done. This completes the first paper. So in the second paper, we shall look at achieving 1 nanometer scale effective oxide thickness using a top gate dielectric on monolayer TMDs with CMOS friendly approach. This is a paper by Eric Pop and Krishna Saraswat from Stanford. So the structure here is simple. It is again a 2D planar transistor. And this paper discusses two techniques to achieve 1 nanometer effective oxide thickness. The first is using silicon seed crystal. The second is using atomic layer deposition of aluminum oxide on this TMD candidate. This is on top of a SOI kind of a wafer. We shall look at how this is done. The first thing is we shall look at how this is done using the silicon seed layer deposition. The TMDs are deposited using chemical vapor deposition on a 90 nanometer SiO2. This SiO2 is thermally grown on this P++ substrate by thermal oxidation, and the deposition temperature for MOS2 is 750 degrees centigrade, while that for WSE2 is at 850 degrees centigrade. And as we saw previously, MOS2 is the NMOS candidate and WSE2 is the PMOS candidate here. And this deposition is followed by active region patterning using xenon fluoride etch. And following this active patterning, this source and drain deposition is done using E-beam evaporation of gold and palladium. And electron beam evaporation is again used for seed layer deposition. And once the seed layer is deposited, this oxide is grown thermally. And once this oxide is grown, atomic layer deposition of HFO2 is done. And once this HFO2 deposition is done, PD is deposited as top gate deposition. And this is the structure of the gate stack. And the first thing which they measured, this is for 0.7 nanometer thickness of silicon seed, which on oxidation gives 1.8 nanometer. And it was observed for WSE2, there was some interesting behavior. So when the top gate bias was 0, it was a typical PMOS kind of a characteristic. It was observed that under top gate 0 bias, there was unipolar behavior, and on shorting the top gate and the back gate, an ambipolar kind of behavior was observed. That is shown by this red curve. And this is attributed to the suboptimal band alignment of WSE2 with SiOX. This also results in this hysteresis, as we see here. And moving forward, the idea of testing with WSE2 required further more analysis of this characteristic. So they claim that they will analyze this in a different paper, and they analyze only for MOS2 based structure, and they analyze for this 0.2 nanometer silicon seed and 0.2 nanometer silicon seed on oxidation, and on top of this oxidation a 5 nanometer HFO2 was deposited, and this effective thickness came out to be about 0.9 nanometer with a very low subthreshold slope of about 70 millivolt per decade. This showed a negligible hysteresis and low VT variation across devices, and this showed a very high ion to I of characteristic as above the order of 10 power 7. So this is the highlight of using this technique. And also on spectroscopy, the apparent difference was not visible between HFO2 and SiOX that has been formed. And now we shall look at using ALOX. So again, on top of the 2D channel, there was a direct deposition of alumina done at 100 degrees centigrade. The precursors used here were tetrahedral aluminium, TEA and H2O. And initially they started out testing by depositing a 6 nanometer aluminium oxide and on top of that a 6 nanometer HFO2. This showed negligible interface defect density and negligible hysteresis as seen here. And the VT variation was also significantly low under forward and reverse sweep. And subsequently, the thickness of the aluminium oxide layer was half from 6 to 3 nanometer. This also resulted in a high on-off ratio of the order of 10 power 6 with negligible hysteresis as seen here. And this also gave sub 100 millivolt per decade subthreshold swing. Now again, the thickness of ALOX was reduced from 3 nanometer to 1.5 nanometer, and it was observed that there was very low hysteresis, sub 100 millivolt, sub 10 millivolt at room temperature, and a subthreshold swing of 80 millivolt per decade was reported at room temperature. And it is claimed that the threshold voltage of the device can be varied by varying this seed crystal thickness or ALOX thickness. It is observed that the seed, as you reduce the thickness of the silicon seed crystal, the threshold voltage decreases, and as you decrease the thickness of the ALOX layer, the threshold voltage increases. So they reason out this by saying that the layer of silicon behaves like positive fixed charges, while that of ALOX behaves like fixed negative charges. So thus the threshold voltage change can be described. And so as this graph also shows the same. And now we shall look at how the effective oxide thickness is estimated. The effective oxide thickness cannot merely be measured from the CV characteristic. This is because the area of the device is significantly low. So the way they characterize the effective oxide thickness is using this technique. The first thing is to obtain the ID versus VTG plots, that is the IDVG curve for different VBG. So the next step for the case of alumina is to plot the threshold voltage versus the backgate voltage at a constant current. This threshold voltage has been estimated at a constant current of 0.1 nanoampere per micrometer, and the slope of this VTTG versus VBG gives a measure of the back oxide capacitance to the front oxide capacitance, and using this ratio the top oxide effective oxide thickness can be measured. So C box by C tox is basically EOT of top oxide by EOT of bottom oxide, and using this metric the effective oxide thickness is estimated to be 1.06 nanometer, and the subthreshold slope is estimated to be 80 millivolt per decade. And similarly, the effective oxide thickness is measured for this 0.2 nanometer SI seed as well, and the estimated EOT in this case is about 0.9 nanometer, and the top oxide leakage current is of the order of 2 microampere per centimeter square, and the subthreshold swing is reported to be 70 millivolt per decade. And both of these effective oxide thicknesses are capacitance effective oxide thicknesses. And moving forward, now we shall look at the conclusion of this paper. The benchmarking of these results were based on top gate leakage current density, and these, as claimed in the paper, are supposedly one of the best reported in literature. In summary, with the seed crystal, the effective oxide thickness is of the order of 0.9 nanometer, subthreshold slope of about 70 millivolt per decade, and a top gate leakage current density of 2 microampere per centimeter square is reported. And with aluminum oxide, an effective oxide thickness of 1 nanometer with a subthreshold swing of 80 millivolt per decade, and a top gate leakage current of up to about 3 microampere per centimeter square is reported. And it is also claimed that these top gate leakage currents are not accurate, as these are limited by the noise floor of the measuring apparatus. And in summary, the paper successfully demonstrates the idea of growing a 1 nanometer effective oxide thickness on TMD channel material. And this paper also presents a low leakage current and good subthreshold swing with a very low hysteresis. And the process flow is compatible with industry standards. And where are we with respect to the future of CMOS scaling with respect to TMDs? Uh, Currently, we see the introduction of 2D nanosheets in 2025, that is the 2 nanometer node of TSMC, and the idea of FinFETs era has already happened. The era of transition metal dichalcogenides is expected to be somewhere in 2037, 2039. That is A2 and sub A2 nodes. And this is a picture by IMEC. So the future of TMDs looks very promising. So with this, I will end this talk. Thank you.